Okay, so let's take a look at the sample problem for how to make use of the impedance. Okay, so actually it says the resistance R is 200 ohm, and the sinusoidal alternative EMF device operates at the amplitude EM equals 36 volt and the frequency FD equals 60 hertz. So what is the potential difference V out of T across the resistor as a function of time, and what is the phasor V out of T? Okay, so so actually this alternating EFF is directly connected to the resistor, so V out of T is nothing but actually this E equals EM36 cosine of omega t. Okay, so this is nothing but 36.0 and then cosine, and then this is omega d is the angular frequency, so we need to have 2 pi times 60. Okay, 2 pi f will be the angular frequency, so and then t. So you can say, okay, V out of T is actually 36.0 cosine of 120 pi T, okay, and then the SI unit will be volt, okay, will be volt. So this is one of the question, so one of the answer to the question. So what is the potential difference V out of T, okay, and then what is the phasor? So for the phasor, okay, actually the phase is 0 degree, so V out will be 36.0 volt. Okay, so this is PT trivial. Okay, for the resistor, so you will say, oh, you can say this is it's an overkill, but yeah, so just let you familiar with it with the easiest case. So for the next one, okay, okay, it also asks you what are the current IRT in the resistor, okay, and then what is the phase, okay. So so I out of T will be V out of T divided by R, okay, so actually obeying the Ohm's law. So this is nothing but 36.0 over 200 and then cosine 120 pi T. So this is nothing but 0.180 cosine 120 pi T, and then the SI unit will be A. Okay, so this is the time domain. Okay, the time domain current. Okay, time domain current going through the resistor, and then the phasor actually. This is also with a 0 phase, so this is nothing but 0.18 A. Okay, so this is also very trivial. So nothing special for the resistor. Okay, just just as intuitive sense. But for the capacitor and inductor, okay, it could be not so straightforward. Okay, but actually if you follow the procedure here, then you can actually make use of it for calculating the steady state, okay, the steady state response. Okay, so here the question will more or less the same. The only difference is here is a capacitor. So capacitor C is 15 μF, and then the other stuff are actually the same. And then what is the potential difference? VC of T across the capacitor across the capacitor, and what is the phasor? Okay, VC. Okay. So here it is nothing different. Okay, it is nothing different. So actually, you can also write out the phasor diagram. The phasor diagram can be like this is the phasor. VC is actually 36 volt, and then this is 1 over j omega d c. Okay, so it will be a complex number. If you plug in all the numbers, it becomes a number, not rather than 1 over j omega c. So actually here VC will be EM, which is 36.0 volts. So actually we can make use of this VC. So VC of T will be 36.0 cosine, and then the omega doesn't change, so 120 pi T here. So volts. Okay, so this is the time domain function. So yeah, so actually it's still very trivial because yeah, this EMF is directly connected to the capacitor. Okay, so for the next question, okay, it asks you what is the current IC going through the capacitor and what is the phasor. So here we can first try to calculate the IC. Okay, so IC will be j omega c VC. Okay, j omega c VC. So this is actually the definition of the impedance. Okay, because CZ is actually VC over IC, which is 1 over j omega c. So actually you can move over this j omega c and then cross multiplication. So IC equals this thing multiplied VC. So here we have a j, and then we have a 120 pi, okay, for the omega, and then C is 15 times 10 to negative 6, and then VC is 36. Okay. Okay, so actually this is J 0.203. Okay, J 0.203. So this is the phasor. Okay, this is the phasor. And then if we need to convert it back to the time domain function, so actually this thing will be 0.203 exponential to j pi over 2. Okay, so actually to memorize the Euler's formula. So actually J is or I is actually exponential to I pi over 2, okay, or J is actually exponential to J pi over 2, 90 degree, okay, 90 degree, but in radian is pi over 2. So actually, converting this thing back to the time domain function will be, okay, IC of t will be 0.203 and then cosine of 120 pi t. The frequency wouldn't change, and then you need to add the phase here. Okay, need to add the phase, go to here, and then this thing go to here. Okay, so this is how we convert the phasor back to time domain function. So for the phasor, okay, for the phasor of a voltage or current, it will be a complex number. So we need to convert this complex number from the Cartesian coordinate, okay, x plus a plus ib, a plus jb, into the polar form. Okay, so turns it into the polar form. Okay, the polar form. Okay, so generally, if you need to convert a complex number into the polar form, will be like r exponential to j theta. So r will be square root of a squared plus b squared, and then theta, tangent theta will be b over a. Okay, so it can be plus pi or minus pi. Okay, So depend on which quadrant it is at. Okay, so actually I write tangent theta equals b over a. So and then you determine the quadrant. Depends on the polarity of a and b. Okay, so this is the current. Okay, if you don't try to use the phasor, okay, actually you can just take the derivative, okay, IC of t equals c dvc dt. Okay, you can actually come up with the same thing, okay, maybe it turns out to be negative sign of something, okay, negative sign of something, okay. Oh. Okay, and then yeah, with j omega. Okay, so actually it turns out to be something like this. Okay, but you here if you make use of the phasor, you don't need the to take the derivative actually. Okay, so we move on to the next one. Okay, so the next one is for the inductor. Okay, is for the inductor. So for the inductor, L is 230 millihenry. Other things are the same. And then what is the potential difference? VL of t. And then what is the VL? Okay, of VL of t. Okay, phasor VL. So the same VL will be EM, which is 36.0 volts. Okay, so this is also the same thing, VL of t will be 36.0 cosine 120 pi t volts. Okay, so this is all the way the same, yeah, because you just connect the alternating EMF directly to the R, to the C, to the L itself. So the potential difference will always be like this. Okay, for the second one, we will make use of the phasor. Okay, so okay, so actually, so for the inductor, IL will be VL over j omega L. Okay, because VL, ZL is actually VL over IL, which is j omega L. So if you just multiply IL to the other side, okay, and move j omega L to here, so you have VL over j omega L. Okay, so so this is 36.0 over j, and then 120 pi. And then L is 230 times 10 to negative third power. So this is the inductance. Okay. So so this is actually negative J 0.45 A. Okay. So this is the phasor. This is the phasor for the current. Okay. For the current of the inductor. Yeah, the phasor of IL of t. Okay. Okay, so if you convert it into the polar form, okay, convert it into polar form, so it turns out to be 0.45 exponential to negative j pi over 2. Okay, so if you still remember, okay, so negative j will be something like this. Okay. So another idea is like you have something negative j 0.45. Okay, so this is this will be the amplitude. Okay, so this is 0.45 goes to here, and then start from here. This is negative pi over 2, so it goes to here. Okay. So this is the polar form, and if we convert it back to the time domain function, IL of t will be 0.45 cosine. Let me see. Okay, 120 pi t minus pi over 2 a. Okay, so this is a time domain function. Okay. So actually this time if you don't use the phasor, it will not be so trivial because you have actually VL of t equals LdIL t dt. Okay, so actually if you have the VL, actually you need to take the integration rather than take the derivative. Okay, so this will be, yeah, a little bit more complicated. Yeah, so actually we can just make use of this phasor so that it will give you what you need. Okay, so these are the three sample problems that tells you how to use the phasor to calculate the steady state response. Okay, the steady state response. Okay, so here come to the next part is the series RLC circuit. Okay, series RLC circuit. So here we still have this RCL. Okay, RCL. Okay, the order isn't really important. Okay, but here we try to connect to a alternative EMF. Okay, so the idea here is it is different from the oscillation. Okay, so the oscillation here is it's like this. Okay, it's like this figure. Okay, we also have RLC. Okay, we also have RLC, but here we don't have any alternative EMF. For this case, we only store some initial energy in the capacitor or in the inductor, so that it will oscillate and then it will finally decaying. Yeah, because we have this exponential to negative pi negative RT over 2L. Okay, so this will this exponent is always negative. Okay, this is always negative, so it when t is larger than 0, so this will always decaying to 0 when t goes large. So but here we don't assume any initial energy. Yeah, we just connect a sinusoidal or cosine. Okay, sinusoidal EMF. Okay, or alternating EMF to this RLC circuit. So it will be different. Okay, it must be different. So here we have a RLC circuit with an external EMF given by E equals to this thing, and then the current is given by this. Okay, this is the phasor. Okay, so I is the amplitude. Actually, the amplitude, and then we have the phase. Okay, and actually for this thing, the total impedance, the total impedance is like we have this E, and then we have R, we have 1 over J omega C, we have inductor J omega L. Okay, all connected in series. So if it is impedance in series, we add them together. If it is impedance in parallel, we use the take the reciprocal and then add them together, take the reciprocal again. So for the parallel impedance, just like following the how to calculate series parallel resistor. Yeah, but for the generally impedance, we can actually doing it like this. So for this RLC circuit, the phasor diagram is look like this. So the total impedance, if we just cut it out and then we look into the right hand side, the total impedance for this RLC circuit will be R plus 1 over J omega C plus J omega L. So RL plus ZR plus ZL plus ZZ. So only this R is the real part. So R plus J, okay, J omega L, J omega DL. Okay, so actually omega DL. Yeah, because we have omega D here. So omega DL, and then just as what I mentioned for many times, 1 over J omega C is negative J over omega C. So J times negative 1 over omega DC. So this is the imaginary part. This is the imaginary part. So you can easily see that, okay, so this thing is actually the absolute value of these parts, okay? So if you just take the absolute value of this complex number, it will be R squared plus the imaginary part omega DL minus 1 over omega DC, omega D, that's omega DC squared, and then take the square root, okay? So this is the absolute value of a complex number. So the real part square, and then plus the imaginary part square, and then take the square root of the whole term. So actually this goes to here. So this is actually the impedance. So the absolute value of the impedance. So this is also the amplitude. The amplitude of the current, amplitude of the impedance will be, this is the amplitude of the V, okay, of the EMF. So this totally makes sense. And then actually for this tangent of phi is here. This is the tangent of phi. This is the tangent of phi. So for the tangent of phi will be here, okay, will be here. So this is the imaginary part over the real part. So here we will be the imaginary part over the real part, and then tangent phi will be this thing. And then for this, z goes to the denominator. So here we have a negative sign here. Okay, so this is the phase. Okay, so if you can understand, okay, how this impedance comes from, okay, how this impedance comes from, then you will be easily understand why this is like that. Okay, we have this will be the absolute value of the impedance. This will be the phase, okay, the phase of the complex number of the impedance. Okay, so here, different from the previous case. Okay, previous case is a damped oscillation. So the frequency, okay, will be slightly lower than the 1 over square root of LC, okay, because it is oscillating freely, okay, depending on the characteristic of the circuit. So the resistor tries to slow down the oscillation, but here this is a linear system. This is RLC are all linear circuit components. So if we provide a sinusoidal input, okay, to a linear system or to a linear circuit, so the output frequency wouldn't change. So here, omega D is still 1 over square root of LC. Okay, so this is the difference. Okay, this is the difference for this. Okay, we have a external EMF here, so the frequency just follow the external source. Okay, and then here it also tells you that for this case it is the condition known as the resonance. Okay, resonance 共振. Okay, the idea here is we try to make the imaginary part zero. We try to make this part zero. We try to make this part zero. The idea here is we try to maximize this stuff. Okay, so for the resonance, we try to maximize Okay, we try to maximize this. Okay, I we cannot change, EM we cannot change. So what we can really change is RLC, we assume they are all fixed value for a specific case. So what we can really change is we try to change the frequency so that we try to minimize this, okay? If we cannot change RLC, but we want to maximize this whole thing, which means we try to minimize the denominator. And then this is a square, this is a square. So they are non-negative values, okay? So if we would like to make it as small as possible, which means that we try to hope, okay, so this thing we cannot change, so we would like to make this thing as close to 0 as possible. So it can be 0, so which means that if we want to make omega d L minus 1 over omega d C to be 0, so we just move over one of the term and then we just cross multiplication. It turns out to be like omega d square equals 1 over LC. Okay, so just move this thing to the right side, move omega d to the left side, move L to the right side. So omega d squared will be like this, and then finally omega d will be 1 over LC. So this is so-called the oscillating frequency, to oscillating frequency. So for the resonance, okay, so for the resonance, we make ZL plus ZC to be 0, make the imaginary part to be 0. In this case, this phi will be 0, which means that the voltage and the current are in phase. Okay, the voltage and current are in phase. For the inductor or for the capacitor, okay, the voltage and the current are 90 degrees off from each other. But here, for the resonance case, this phi is 0, so the voltage and the current are in phase. So in this case, the current is in phase, okay, with this omega d. Okay, so if omega d is equal to this thing, okay, so this circuit is resonance. It achieves a maximum amplitude of the oscillation. Okay, so actually we can use the potential method to really get similar things. Okay, actually I don't try to go through the whole procedure, but try to let you understand. Okay, if we don't make use of the phasor, okay, how complicated it will be. So here we have this E is actually EM cosine of omega dt. Okay, so it will be equal to, this is VR, this is VC, this is VL. Okay, so it will be VR plus VC plus VL. Okay, so and then we also assume that the whole current loop is I. So for VR will be R times I, and then for VC is nothing but VC itself. And then for the VL will be L di dt. Okay, so here we also have I equals C d VC dt. So yeah, so this is what we have here. And actually, we try to, okay, I try to copy it down. Okay, for this thing, we try to, yeah, so hopefully we try to make it an I. Okay, so what we need to do to convert this thing to here is like, we try to take the derivative and then multiply by C. Okay, so for this thing, we multiply by C, and then we take the derivative for the whole thing. Okay, of course, this thing should be put in the front. Okay, but yeah, I don't have enough space. Okay, so just let you know, we try to make something like this. Okay, for this equation. Okay, so it turns out to be negative omega d em sine of omega dt. Okay. And also we have the C, okay, so put it here, okay. So just take the derivative, okay, take the derivative cosine turn to negative sign, and then for the chain rule, we have omega d in the front. We also multiply by c, so the c goes to here. So this is pretty much like this. And then for the remaining stuff, it will be easier. So r times c, and then we have a di dt. Okay, so it's very trivial. And then for the second one, c dv c dt. Okay, just what we want to construct. So c dv c dt is nothing but I. So it turns out to be an I. Okay, and then finally, LC d 2I dt2. Okay, because it's already first derivative. Okay, so take one more derivative will be second derivative, and then L times C go to the front as the coefficient. So we try to divide LC on both sides. So we have a d2I dt2, and then plus this is the first derivative. RC over LC will be R over L, and then di dt. And then finally, 1 over LC I equals negative omega d em, and then C cancel with one of the C, and then with a L here, and then sine of omega dt. Okay, so the idea here is like we need to solve this second order linear coefficient ODE. Okay, so by solving this, you need to first find the homogeneous solution. So it will be like S squared plus R over L, and then S plus 1 over LC equals 0. And then you also need to expect B squared minus 4AC is less than 0, which is B squared is R squared over L squared minus 4 over LC is less than 0. So this is the condition for oscillation. Okay, so R should be small, and then you will be able to calculate the S to be a complex number. S to be a complex number. So I don't try to go through the whole procedure. So it turns out to be like S will be like alpha plus J beta. Okay, so so you will get the complementary solution to be like IC of T. IC of T will be like let me see, exponential to alpha T, and then A cosine of beta T plus B sine beta T. So this will be the complementary solution. And then if we, okay, actually this alpha will be less than 0. This alpha will be less than 0 because this is positive. So when t goes to infinity, so this thing will tend to 0. Okay, so for the steady state, we just ignore this part. Okay, we just ignore this part. But finally, we still need to get the VP. Okay, so the VP of I mean the IP. The particular solution will be like still a C cosine of omega dt plus D sine omega dt. And then you need to plug in this thing back to here to solve for C and D. So this will be a very tedious work. So of course I don't try to go through it here. But actually, if you're interested, you try to go through it, then you'll be able to find that. Okay, so finally, you will get I will be like that. And then the phi will be actually look like this, and then you will also get, okay, so you will get something like that. So showing this is just to let you know if we want to get the steady state. Okay, so for the steady state, okay, we don't need to go through the procedure for solving the ODE. Okay, if you want a complete solution, of course you can check out the ODE, and then you also can find the the transient, okay, the transient response, okay. So this is only transient, 只是一个暂态, okay. So it won't last forever, okay. So it will always decaying, okay, depending on how large this alpha is, okay, how large this alpha is. So but the idea is for the steady state, okay, for the steady state, which means when t is large enough, we can make use of the phasor. Then it can help us. Yeah, we just need to, according to the formula, just plug in all the number RLC, and then we can just, get the expression very quickly. Okay, so here is an example to see how we can make use of it. So here we have a R, we have a C, we have L, and then we also have FD, and then we have EM. So it asks what is the amplitude of the current phasor. Okay, so this is so actually we can always write out C will be R plus J omega dL minus 1 over omega dC. Okay, so this is nothing but 200 plus J, and then 60 hertz is 120 pi. Okay, and then L is 230 times 10 to negative third power, and then minus 1 over 120 pi, and then C is 15 times 10 to negative 6 power. Okay, so this is the impedance. Okay, this is the impedance. Actually, you can just press the calculator to find that out. This is actually 200 minus J 90.13. Okay, so it turns out to be a complex number, so which is not that difficult to handle, at least comparing to solving the ODE. Okay, so and maybe for some of the calculator you can just let the calculator to compute the complex number for you. Okay, so actually I will be EM over the Z, okay, which is actually 36.0 over 200 minus J 90.13. Okay, so actually it asks you the amplitude, so which means that we need to take the absolute value of this phasor, so to make it like 36.0 over 200 square plus 90.13 square, and then take the square root. Okay, make it like this. So it is actually 0.1648. Okay, so this is the amplitude. This is the amplitude. This is the amplitude of the current going through this RLC circuit. And actually, for the absolute value, okay, for the absolute value, when you try to, let's say, when you have two complex numbers multiply together and then take the absolute value, it will be nothing but taking the absolute value first and then multiply the absolute values together. So here is the case. Division is like multiplying the reciprocal of one of the complex numbers. So it will be like, the absolute value of 36 is 36, okay, is 36. And then the absolute value here will be like 200 square plus 90.13 square, and then take the square root. So you don't need to rationalize this, okay? You don't need to like multiply 200 plus J 90.13 for both the denominator and numerator, and then turns out to be so the complex number with the proper form, and then try to calculate the absolute value later on. So you just need to calculate the absolute value for the numerator and denominator individually, and then divide them. Okay, so so it asks you what is the current phase, what is the phase of the current phasor I, okay? So for the current phasor, so just now we have this Z to be 200 minus J 90.13, okay? So just recalling this result. So phi will be arctangent of negative 90.13 over 200. Okay, so the imaginary part divided by the real part. And then you press the calculator, will be 24.3, negative 24.3 degree, or negative 0.424 radian. To convert to a radian, you have the something in degree divided by 180 degree times pi. Okay, so it would be the convert an angle in degree to radian. Okay, so this is the phase. This is the phase. You can just answer either of them. Okay, so here is the power in AC. Okay, so maybe we just take a 10 minutes break.